In this section, we'll study the least squares method. The section begins with a definition. For a given data set, a collection of points, P of x is a continuous function. The continuous function P is an interpolation if it passes all the data points. P is an approximation if it approximates the data points. In other words, an interpolation is a continuous function which passes all the data points. An approximation is a representation of the data set. Let's see this example. A data set is made in this way. This data set is a perturbation from a straight line, as in this script. And we choose M. There will be N 10 points. And X value in the first column, and I is moving from 1 to M, which is 10. And Y value in the second column is I, N, using random integer generator. And this value will be between -1 to 1 divided by N here. So it is a perturbation from a straight line. That is a scatter plot. For this data set, you can construct an interpolation passing all the points. Then it will be 9th degree polynomial. And if you try to represent by a line, then that is a least squares line. Here we plot together, and the blue one is the interpolating polynomial, and black straight line is the least squares approximation. Interpolation is often too oscillatory to be useful. Furthermore, it may not be defined, particularly when for one X value there are more than one Y values, then you cannot get an interpolating polynomial, right? Okay, we formulate the least squares problem. A is an n by n metric. Then Ax equals B, this linear system, may have no solution, particularly when m is larger than n. In reality, m is much larger than n. Usually, m represents the number of data points, and n denotes the data dimension. If even though we don't have a solution, we may try to find the best solution so that Ax and B, the difference is as small as possible. That's the least squares problem. Okay, let's define the problem mathematically in this definition. A is n by n metric. M is larger than or equal to n, and B is a vector in Rm. Then the least squares problem is to find x hat in Rn, which minimizes this difference, Ax minus B, measured in L2 norm. So we can write in this way. Its minimizer argument is x hat. Now, rather than L2 norm itself, we may try to use norm squared. Mathematically, no problem. once it is minimized, then its square must be minimized. And if the square is minimized, then this term must be minimized. The reason we try to formulate in this way is that we want to ignore the square root so that we can use the calculus technique more conveniently. Here, x hat is called least squares solution with the linear system. Okay. For all x in Rn, Ax will be necessarily in column space of A, must be. Here, metric vector computation can be expressed as a linear combination of columns of A. And if A is given A1 to AN, n columns, and X is from here X1 to Xn, so AX, thereon, then it can be written in this way: X1 and A1 plus X2, A2 plus, and then there is now Xn, AN. So it is a linear combination of the columns of A. So that AX, for any X, AX must be in column space of A. Right? Okay. And so that here, the finding least square solution is the same as to seek on X, then makes AX the closest point in column space of A. So we can formulate in this way. We try to project B onto the column space of A, so that is called the B hat, and then we try to solve AX equals B. Now B hat is in the column space of A. This linear system should have a solution, at least one solution. And now, if we have a solution, then it will satisfy that one. So in this case, X hat is on least square solution of the linear system. So pictorially, we can express in this way. Now, this is now Rn, and along with the metric, it's transformed into Rm. Then column space of A will be a subspace of Rm. Now, for arbitrary B, once B is not in this column space, then the linear system has no solution. We try to project B onto this column space of A, then we can find X hat some point such that Ax hat must be B hat. So that is least square solution. The quantity here from here to there, that is B minus B hat, which is same as B minus Ax hat. Is called the least squares error. That means B minus Ax hat, the distance, is smallest among here B minus Ax. So if you try to measure from B to any point on in the column space A, then this distance will be less than or equal to this distance, right? Okay. If A is square metric and invertible, then AXB has a unique solution, we know that, and then the least squares error must be 0. That is quite simple result. Okay, for the least squares problem, here quite popular technique is the method of normal equations. Let's see how we can get the normal equations. The set of least square solution of ax equals b coincides with the non-empty set of solutions of the normal equations. So rather than ax equals b, we may consider that equation. This is called the normal equations. Here the logic is quite simple. Now, we assume that x hat is the least square solution. Okay, b hat is projection of b onto w. Okay, so x hat is a least square solution. Then, now b minus b hat, that is same as b minus ax hat, that must be orthogonal to column space of A. As you can see from this picture, now b minus b hat is orthogonal to the column space of A. So that for any column aj, if we apply the dot product and aj and b minus ax hat, then that must be 0, because this one is orthogonal to any linear combination of the columns of A. So for each column, the dot product must be 0. That is, rather than dot product notation, we may consider transpose, the vector transpose, and the same. And now we try to combine every vector. So rather than single vector, the column, we consider whole matrix. Then here aj transpose, a collection of this will be here A transpose. So it is 0. So that is the same as this one. And the other direction also the same. So that eventually least square solution of ax equals b is a solution of the normal equations. Okay. Okay. Now we have question. From this one, we reach that one. The thing is, now A hat, A transpose A, that one must be in R n by n. That is a square metric, and also it must be symmetric. The problem is, if it is not invertible, then yet we have some difficulties to find x. Okay, so the remark is saying about that. When A transpose A is not invertible, the normal equations have either no solution or infinitely many solutions. That's the reason data acquisition is important to make it invertible. So depending on data acquisition, the system can be invertible or it may not be invertible. Okay. Now we have a theorem for the method of normal equations. A, the metric, m by n metric, m is larger than or equal to n, then these three statements are equivalent. The equation ax equals b has a unique Okay, here this is unique least squares solution for every possible B. That's one first statement. And here the columns of A are linear independent. Okay, so once the original matrix and the columns of A are linear independent, then this linear system has a unique least solution, which means that A transpose A is invertible. Once it is invertible, then the solution must be unique. Right? So here, the final one is the matrix A transpose A is invertible. So to find a unique least square solution, and you may check either A transpose A is invertible or the columns of A are linearly independent. But checking this one may not be easy. But columns of A, you can easily check if they are linearly independent. So that probably for uniqueness of the least square solutions, you may check the columns of A. Okay, this is the practical way to see if there is a unique least square solution. In this case, once it is unique, then by inverting the matrix A transpose A, you can find the unique solution. Okay. Compared with this one, okay, original equation is A, x equals B, and once it's invertible, then x is now A inverse B. Okay, this one is inverse of A. Now in front of B, this portion has the role of A inverse, but there's no A inverse for general size matrix. So it looks like inverse. So we call this portion the pseudo inverse of the matrix A. So by using A plus, we try to here define this part. So that is the pseudo inverse of the matrix A. Okay. Okay, we have an example. Describe all least square solutions of the equation AX equals B, given A is here, B is here. Apparently, so that once we try to use the equation of method of normal equations, okay, so that A transpose A, X equal A transpose B, right? Then we have to make, if we want to get the unique solution, and that must be invertible, which is the same as the columns of A are linearly independent. Let's see columns. And if we add these two columns, then becomes the first column, which means A is not, okay, columns of A are not linearly independent. So that once you try to solve these the normal equations, then you will be more than one solution once you have a solution. So that either it has a solution, no solution, or infinitely many solutions. For this problem, we'll have infinitely many solutions. Okay, let's look at code. Read it in MathLab, and I'll use Octave. Okay, here we have, okay, that is, okay, here. Now, we defined A. There's the first column is 1 and 1, 1, 0, 0, 0, 0, 1, 1. And B is a column vector. And here in this program, we'll see if AX equal B has a solution. Once it has a solution, then we call it consistent. So through reduced echelon form, we'll try to see if it has a solution. And of course, it has no solution. Yeah, we'll see it. Now, for least square solution, we organize A transpose A and A transpose B, and we try to invert A transpose A, try to inverse A transpose A, then we can get a solution. But we see what happened. And rather than that, here A transpose A and A transpose B, and we'll try to get augmented matrix and try to get reduced echelon form. Okay, let's execute. F of 5 is usually, okay, that is run, that is, and now F5 is the run, so I'll hit F5. Then, now in command window, you can see the result. Okay, here, for consistency, there's augmented matrix from A and B, and this row is saying that left-hand side, so here 0x1, 0x2, 0x3, summation is 1. So left-hand side is always 0, right side is 1. That is impossible. So that there's no solution for AX equals B. So the B is not in the column space of A. Now we start least square solution and we try to inverse A transpose A. Now that matrix singular, so that here the computer generates this solution. It's a solution, fortunately, but once it is singular, then we cannot expect a right answer, but it'll be a solution in this case. Now that one is augmented matrix. It's basically coming from here A transpose A and A transpose B, and that is augmented matrix. Okay, here we have that one. In fact, this one, and then reduce the echelon form. Okay, that is this one, and then this is reduced echelon form. There are two the pivots, and then x3 is a free variable, and this one, and this is fortunately 0, so that we'll have infinitely many solutions. Okay, so that is copied here for A transpose A and A transpose B. The augmented matrix will try to get the reduced echelon form, so we recheck that one. Okay, now the first line means that there's x1 plus x3 is 5, so we can write in this way. x1 is the same as 5 minus x1. We are moving this one to the other side, and the second line, second row is saying x2 is minus 3 plus x1. Oh, okay, that's x3 now. x3. Now here x3 is a free variable, so you can write here there's x3, and then from this one there's x, x1, x2, x3, and then constant vector, so 5 minus 3, and final component is 0, And then this column is making, along with x3, a free variable. You can choose arbitrarily, and that is a -1, 1, and 1. Right? So we recheck this one. Okay, this has all the solutions, all the least squares solutions of the equation ax equals b. And for every choice, it'll be a solution. Now, once you are choosing for this one, for example, x3 equal 8/3, okay, then you can get that solution. Okay, that solution is a special solution. Now, the matrix is not invertible, but for every computation, you cannot expect this one. Once it is not invertible, then you cannot get a solution in most cases. But for this one, somehow it produces a solution. Okay. Okay. For given system ax equals b, we try to solve it through least squares formulation, so that j of x is ax minus b squared. Now, so the thing is, we originally tried to solve that one, but now A transpose A, X, and A transpose B, that is normal equations. We'll try to get these normal equations by using calculus technique. So we start with this objective function, this term, named j of x. Then we can write in this way, ax minus b. Of course, this is a vector, so that it's transpose and ax minus b. And x hat is a minimizer of this functional j of x. Then here we can see in this way, we try to make derivative, so this gradient, and once x is replaced by x hat, then that'll be 0, because at x hat, the value is minimum, and this is a kind of quadratic, so that the gradient must be 0. So let's try to compute the gradient of the functional j. Okay, here the gradient is now for this term. We try to write down here the expanded terms. So if you expand, then you will get this one. Now, for each term, we try to apply gradient. And you can do it in detail, but you may think this one as a scalar values. So for example, that is like a transpose a x squared. So the x derivative is now, for this x squared, we have 2x. And for that one, that is minus 2x a transpose b. This is constant. And then the derivative of this term is minus 2. And this is now, there's no x involved, so x derivative must be 0. So by considering these scalars, you can get this one quite easily. But it's not scalar values. But by using some vector manipulation, you can reach this one exactly the same way. Okay, now it is 0. When x hat is 0, then it's 0. Then that is exactly same as that one. Right? So the normal equation can be obtained by using the method of calculus. But earlier, by using some the properties, and we try to get the normalization. So original linear system, the solution must be same as the solution of normalizations. But normalizations can be obtained through this technique, or through the method of calculus. Okay? That's the end of section 6.2. Thank you.